Hello and welcome to our second week of the 4E summer school. I hope you have had a nice weekend, and today we will start with the topic evaluating and checking test data and interpretation of typical test results. So let us start with the topic, the new efficient dynamic tensile test. And I will talk about the tensile test itself. As you have seen the test before, I will explain why I think that the test is really easy to handle and we can conduct the test very easy. The test consists, the hardware consists out of main three parts. These three parts are the counter-bearing system, as you can see here on the left corner. And the second part is the sample clamping. This means that we do not fix the test piece directly on the counter-bearing system with screws or so on. So we fix the test piece in a clamping system in some jigs that we easily can hang in the counter-bearing system. And of course, on our pendulum, we have to use a third part. This is the pendulum impact head that we have to change from the standard 3-point bending head with just 2 screws to the tensile impact head, as you can see here. And this makes the operation really simple because there are not many screws that you have to fix. It's just hanging in the test piece with the clamping system. But you will really see it in the live test afterwards. Let us talk about the measurement technique of the tensile test. As you know, in every test, we are using, in the normal pendulum test, we are using acceleration sensors on the pendulum head to calculate the force. In this tensile test, it's a little bit different. In this test, we are using directly a piezo load cell with a full scale of 20 kilonewton. This is one channel that we are recording. Of course, we have to think about the time channel because it's really important that we get time synchronous data also with the stroke channel. And this right diagram should show this a little bit, that it's quite important to get all different channels on the same time x. And for the now we have to talk about the stroke measurement. We do it with an incremental angle sensor in the top of the pendulum in the standard test setups for 3-point bending or puncture test or so on. But in a tensile test, it's quite important to use a DIC system to measure the local strain on the test piece. And this could be very complex and quite difficult if you do not have a well-prepared system. And now I would like to show you on other 2 slides how we can handle this DIC system on our IMPETUS pendulum. So we have to think about the correct time synchronous data. That means, as I have shown before, we measure force, we are recording the time, and we have to trigger the camera, the high-speed camera, and of course we have to trigger the lights. How do we do that? Our pendulum has a 5-volt trigger output where we can connect the high-speed camera. We are actually using in our lab the Photron Nova S9. It's a really good high-speed camera with a compact dimensions that we have included in our software. As well as we have connected the high-speed camera to our pendulum, we also have linked some flashlights, some LED lights because when we are thinking of high-speed image recording, we have to use really bright lights that we get enough light on the test piece. And you can't just switch on this light and shine on your test piece, because we are experts in plastics and we all know that there is a big assumption to heat. So we just got a small flash during the test that we don't heat up our test piece. And all this data will be stored in VALIMAT. And the second software, which we see here on this slide, is Mercury. Mercury is an external DIC software, which is really good linked to VALIMAT. The next thing is what we should think about is the calibration of the DIC recording. Many of you who have ever used a DIC system know that there is a big effort to get a good calibration of the DIC system. And we have solved this problem with a predefined camera position fixed mounted on our pendulum. So we have defined a position 1 and a position 2, where we can easily switch the camera from one to the another position and get always a right calibrated camera image to our tensile test. That means we have provided a template where we have stored the calibration 1 and calibration 2, so we can easy and fast go to test. And the third thing what we should think about is the handling of the recorded data. Because now we can really good measure the DIC, the local strain on our test piece, and that we can handle this data in VALIMAT. We have a so-called 4A standard DIC nomenclature. That means that we have defined some measurement points in the software Mercury. Here you can see some crosses, some sections where we measure the local strain, and each section has a predefined name with an ID which can handle this ID in VALIMAT. That means we are measuring the longitudinal and transversal local strain with this predefined DIC standard. And we can automatically give this data to VALIMAT, and VALIMAT knows which strain we have to evaluate. But more on that you will see afterwards in importing the data, and also when we do the live test, what it is mentioned. Okay, to sum up these points, I would say it's not complicated to measure DIC with the VALIMAT system, because we have the 5-volt trigger output and get a time synchronous data. We have a very good predefined camera position on the pendulum. That means that we do not have to calibrate each time we go to test. And we have the DIC standard nomenclature from 4A, which makes it easy to handle the big amount of data in VALIMAT. And this all leads to a very efficient dynamic testing, I think. Now on this slide, I will just show you a quick which steps do we have to do in our dynamic tensile test. And I have split it up into steps which have to be done manually and steps which are done automatically by the software. Of course, we have to do a good sample preparation with this backlit pattern. Therefore, we spray white and black color on our test pieces that we got a really good speckle pattern. The second step is to fix the test piece in our chicks. Then we can just hang in the fixed test piece in the counter pairing system, and all other things are done automatically. That means after hanging in the test piece and pulling up the pendulum arm, we activate automatically the bright lights, the flashlights. We're starting the recording of the high-speed camera, and after the test, the images will be automatically downloaded to the software Mercury. Mercury will evaluate the strain field like that and automatically copy the results to VALIMAT and store it in one dataset. Okay, and this slide is just to sum up some results, what we have done with some external partner where we have tested on an external machine, and we have compared these results to results from the 4E IMPETUS machine. We have tested some unreinforced plastics on 3 meters per second, 3 types of unreinforced plastics, and you see the really good correlation of the red and blue results on the external results and the 4E IMPETUS results. And of course, we can also test some reinforced plastics. Here you can see a reinforced plastic with a fiber reinforced of 30% with a kind support of Celanese, where we have tested 0° and 90° test pieces and also got a good correlation on that plastics. And now we have talked enough, I think, and I will show you these steps in a live test on our pendulum. Okay, now we are here live on the hardware. If you don't know the hardware, you see here our IMPETUS impact pendulum, the dynamic testing machine with our pendulum arm and with the setup of the tensile impact test. What we have to do to test on this tension test, we have prepared some samples, some unreinforced plastics. I will show it to you. We have prepared these samples with our speckle pattern. It's a norm tensile test. And now we have to fix this sample in our jigs to test. Therefore, we have to mount the test piece with our sample clamping. We are using 4 screws, therefore, for that. Just insert the test piece. And fix it. This should work really fast and easy. Okay, just fix it. And the last 2 screws. And now the test piece, what we will test, is prepared. Now we have prepared it. And the big advantage of this system is that now if we would do the test not on room temperature in the standard climate, if we would do tests on a high temperature or low temperature, we just can go to the oven, put it in, and heat up the sample. And we also can, after that, conduct high or low temperature tests. Today we will do a room temperature test. And so I just can take this sample and hang it in our counterbearing system with like that. And now the test piece is fixed in the system. As you know, we always have to bring the pendulum arm in contact with our test piece and close the door. So we have prepared the hardware. Now I will switch to the software and show the settings of the software. And here you can see our software VALIMAT. I will switch to the tensile tests right here. And here we have prepared some tensile test settings, what we have to set up. I will switch to the big window. On the left corner, you see the counterbearing system camera in the test, in the IMPETUS system. Here we have prepared the test. It's a tensile test. We will conduct the test with a velocity of 3 meters per second. We have a distance support length of 30 millimeter and defined some dimensions of the test piece. Okay, and now we have to go to the measurement settings. We are in contact with our test piece. We can go to the contact angle and to set angle, and we are raising the pendulum arm up to 3 meters per second. The pendulum arm stops automatically on the right position. We can go to start. VALIMAT ask if the safety screen is closed for sure. Here we can see the correct test data. This is the report, which is stored on each test. And we can start the test. Okay, now we see the hardware again. So the green button is shows us that we are ready to measure. I switch on the light on the low level, and I will conduct the test. And now the test is conducted. We are switching back to the software. The images are still downloaded on the system. Okay. Now the images are, the DSE is calculated automatically in the background, as you can see here. Oh, sorry, I have to switch in the full mode. The DSE image is evaluated automatically in the background, so I do not have to do further manual steps. Okay. Here we are reaching more than 200% strain because in this field we got to a clear failure, and the recording will just be finished in a few seconds. Now the recording is finished. We are automatically creating a video. See it again. And it fails. Okay, now we are copying the data to the dataset in VALIMAT, and everything is stored. Here we can see directly our, here we can see the results, which raw data we have imported from this measurement. We see the acceleration signal from which is recorded from the sensor here in the background, the acceleration sensor on the pendulum head. We see the displacement, it's calculated from the DSC. Also the local strain measuring and the angle sensor and the force. I just will show you the result of the local DSC strain measurement. And now I will calculate we will evaluate this test. Therefore, I just have to go to evaluate. And I directly can plot this test in the screen. And we got our result. It's the force displacement or the stress strain curve, as we can see here. Okay, and I can easily compare these results directly with the static results which we have performed on a quasi-static machine, and we see a really good correlation of these results and the big influence of the high strain rate which we can reach on the IMPETUS system in the force displacement or also directly in the stress strain. Okay, and just to show you how fast this test was conducted, I will perform one test again. So I have to select the one dataset. I will select a new dataset right here. Hang in this the test piece. Go in contact. I close the door and raise the arm up to the 3 meters per second. And can perform the test. The test is performed. The images will be downloaded. I just have to pull out the sample. The sample looks like that. Meanwhile, the TSC is computing. As you can see, TSC will be, the computation of the TSC will be finished. Sorry for the scaling problem. I have to scale the full field area a little bit higher. And we have finished the test. Okay, and that is the whole procedure, what we have to do in the dynamic tensile test. I hope you got a good impression how we deal with this topic. And we're nearly finished with this test. And that's it. And we have our result. Okay, so let us switch back to the presentation and we will continue with another topic. Okay, and as I've mentioned before, now I will show you how we can import external test data, as you have seen just before, for example, the static tensile tests or static 3-point bending tests or something like that. First of all, it's important to mention that we have included in our software two different import possibilities that we can use. We have for a standard import and we have an ASCII Excel import. That means for a standard import is really well prepared for handling tensile tests with some DSC measuring channels. In this standard import, we have a predefined designation of really quite big amount of channels. That means we always knew that the time channel has the designation, for example, 000 underscore time, or all local strain in X, Y, and Z direction. What we get, we starting always with a number of 400, and this is for a DSC standard designation, which we can provide you if you need external data to import in your system. I will switch in the software to VALIMAT directly, where I will give you an example how we can import some external test data. Okay, now we are here in the VALIMAT software again, and I just quickly will show you how we can import such a DSC standard. Therefore, I will just import a tensile test. What we have to do is to add a new data set where we can predefine which test we have. We have to set it to a tensile test. It's a static test with a sorry. Okay, we defined it a static test with a velocity of 1 millimeter per second. And if we have done this, we can easily copy this test with copy and add 5. So we have decided it once, copied it 5 times. Now we have to add some information about the test pieces. As you have seen in a session before, we can easily copy our data sets from VALIMAT to an Excel, for example, and we can easily add some prepared data. I will show it to you. Data. I have prepared this data, tensile test, dimensions, and I just can take the prepared dimensions of the test piece and easily insert it in our database. Import database values from clipboard. And now we have added our correct dimensions of the test pieces. And now we can go to measurement, import, and use for a standard import. And we select the CSV files to what we would like to import. We go to open and we will see the import mask. In this mask, we have the match between the specimen name and the file name. so it's matched correctly. And here in this table, you see which channels were found, what we would like to import. We find a crosshead, we find a technically 2-point strain, and we found some local true strain local channels. And now we can import this file by clicking OK. And the import is done. When we go back and have a look, the symbol has changed to a green symbol. I will explain the symbols later in detail. And now we see here in the measurement curve row data file, we have our imported channels with the local strain measuring included. And the last step is I will show the import of an ASCII file, for example, or a text file. That I will do it on a 3-point bending test. Therefore, I copy a test from a 3-point bending 5 times. I also have to add the correct sample dimensions and the correct name of the test piece. I've prepared it in one Excel, which I have measured before. So I just copy the informations, what I would like to import, and insert it here, import database values. Now I have the correct name and dimensions of the data, of the data set. And I can go to the measurement, import ASCII and Excel. Now we got a slightly different mask. In this mask, I have to select the file. Now I will select one file. I can show it to you before. What it looks like. In this file, we have the name of the test piece and always the channel time, force, and stroke. And when we select this file, we got a good preview in this window, and we have just to define which file we are using. We have a header of 3 rows, a header. The label row is in the 2nd row, and the unit row, where the units are defined, is in the 3rd row. We are using a dot as decimal separator, and we're using the tabulator as column separator. And if we have selected this file format quite freely, we can go to parse unit, and the software matches correct the channels to import. And if I go to OK, I have imported the 3-point bending tests, as you can see here, with a stroke and force channel. Okay, now we have finished the import. The last topic we'll talk today is the evaluating and checking test data, and we just will give you 1-2 examples to interpret the typical result of a dynamic test. What we are dealing with in VALIMAT. In VALIMAT, in the upper left corner in the first window, there we have the evaluation settings. And in this evaluation settings, we will talk about the filtering of test data, about the evaluation of the displacement, about the evaluation of the velocity. A very big and important topic is the 0-point evaluation. And of course, we will talk about the identification of failure, about the stress strain evaluation, and the last point will be the results, what we got directly out of VALIMAT and how we can handle with it. So give me some basic informations of a test. As you have seen before in our software, in the upper left corner, you can see 3 type of symbols at the test. And these symbols give you some information about the status of the test. So if we create a new data set, we got this blue symbol. That means that we have a new data set without any raw data in it. And for sure, it is an approved data set. That means this gray symbol with this blue symbol. The next level of a test is this green pendulum arm. This green pendulum arm will be shown if we have performed a test on the pendulum itself, or we have imported external test data, as you have seen before. If you can remember, after the importing, we have seen all these green symbols. That means that there are stored data in this data set. And after we have reached the green symbol, we can evaluate a test. To evaluate a test, there are two possibilities. If we click on I gave a right click on a data set, we came to evaluate, and we see evaluate and evaluation default. This evaluation default means that we got a default setting on the evaluation on this data set. And after the evaluation, the symbol of the green pendulum changes to this blue calculator. But we will see it in the software live afterwards. And the third symbol in our left upper corner on the data set right here is this symbol. This gave you information about the behavior of the test and how the test piece came to reach a failure or not. The first symbol is this green symbol. It's a recovery. That means that we have, for example, a 3-point bending of a ductile unreinforced plastic. We have performed this test and we got a load, and after a few millimeters we got an unloading in this test. That means we have a recovery of the test piece. This shows you that symbol. The next symbol is this symbol. That means a deformed specimen, and you reach this symbol if we got a deformation, a plastic deformation, and pulls the test piece in the 3-point bending, pulls through the counterbearing system. That means we have more energy in the test and came not to a recovery, so we pull through the test piece of the counterbearing system. And the last symbol is this blue symbol, and this means a clear failure was detected. Here we have an example of a fiber reinforced plastic in a 3-point bending test, and for sure we see here a really big drop of the force, and so the software can detect a clear failure. Of course, we can change these symbols by ourselves, but I will show it to you in the software afterwards. And the last symbol we have here is the orange M. This means we have set the failure manually. Okay, but now let us start with the first topic of the evaluation, and this is the correct filtering of the measurement data. Therefore, I will switch back to the software. Okay, now we are back in VALIMAT, and I will show you some evaluation settings. I will show the first settings I will show to you in an example of a 3-point bending test of a fiber reinforced plastic. Therefore, we open the data set. I hope now you can see it better. We have a fiber reinforced dataset. We performed a 3-point bending test on our pendulum system with 3 meter per second. And now we're here on the last point on the evaluation, what we will have a deeper look on. Here you can see the setting of the filter and what is the possibility of this filter. Now we have a CFC velocity optimum. This is an automatic filter which is decided from the software depending on the decided velocity in the test. So we have done a 3 meter per second test, and the software decided this velocity optimum, and this CFC filter is a CFC 2500 filter, as you can see in the rotator. Here you can see the decided filter. A quite important point here in VALIMAT is that VALIMAT always stores the unfiltered rotator in a separate file in the backend structure. That means we always can evaluate a test again and again, change the evaluation settings, and also, for example, changing the filter settings and just evaluate again. I will show it to you. So now I will plot this 3-point bending test with a filter of 2500 CFC. This is a good filter for that really brittle material. And now I will show it to you what happens if we change the filter to a lower level. Therefore, I just open the drop-down menu and go in an extreme filter, for example, 600 CFC. Now I have selected this filter. I go to save. Now the setting is saved, and just came to evaluate. I will re-evaluate this with the settings, and now it is re-evaluated. Now I can plot this curve, and you can directly see the difference between these two types of filter. The blue curve is the 2500 filter, and the green curve is the 600 CFC filter. For sure, you can easily evaluate in this green curve a good Young's modulus, but you will get a problem if you will evaluate the correct failure point on this very strong filtered data set. So you always have to keep in mind what you will do with your tests afterwards. So it wouldn't make sense to select this strong filter of the green curve in this example. I will prefer the 2500 filter, which is also decided automatically by the software. This is the filter settings. I will change back the filter again, that we can go further. Okay. The next point we will talk about is the evaluation of the displacement. Is the second part in the evaluation, and I will shortly show you what we can do in this evaluation. The second point is the evaluation of the displacement, as I have mentioned. Sorry. The displacement could be evaluated on the angle sensors and the acceleration. The difference is that we can have a look on our raw data. As you know, in the normal pendulum test, we got a channel, it's an angle sensor, and we got the displacement of the pendulum arm. And with the default setting, we got the evaluation out of the angle sensor, but we also can change it to an acceleration sensor. The third part, what we have to look on it, is the evaluation of the velocity. The velocity will also be evaluated on the angle sensor, as we have seen before. And that means that we decide a target velocity of 3 meters per second. And as you can see here in this 3-point bending test, we have reached an actual velocity of 2.98 meters per second. So really, really close to the target of 3 meters per second. But if we have some troubles with the evaluation of the velocity on external test data or something like that, we also can change it to a manual side and decide the velocity manually. What is also important to mention that if we have a look on the evaluation of the displacement, this evaluation settings is always depending on which test method we have selected here. So if we change the test method from 3-point bending, for example, to a tensile test, or we change the test method from a dynamic test to a static test, the evaluation settings will change. I will show it to you. So now we have a dynamic test, and if we have a look on a static test, for example, it's a tensile test, we have other possibilities to evaluate the velocity for sure, because there we have in the static test we have no angle sensor as we have it in the IMPETUS system. Here we can evaluate the velocity of the static gradient at the beginning, that means on the crosshead, or we can displacement a static average over the whole displacement, for example. But let us switch back to the 3-point bending example as we have seen before. In this example, the next evaluation step is the 0-point evaluation. In this 0-point evaluation, we have also several possibilities. The default evaluation setting is the number 5, the acceleration signal without filter. That means we got the evaluation out of the raw data of our red curve, of this curve of the acceleration signal right here. And I will plot this curve again that we can see it. This is this curve, and sometimes the 0-point doesn't match together. For example, if you will compare static and dynamic tests, and if you will change the 0-point, you have the possibility to change this 0-point evaluation. For the static tests, I will prefer, for example, the 0.7, the extrapolation force displacement gradient curve. Or we can select a contact angle or something like that. But now I will show it to you in the manual way. I change the 0-point to manual, and I will take a manual timestamp for the 0-point. And how can we do that? Therefore, switching in the measurement tab on the right side. Here we are at the measurement tab, and in this measurement tab there is an important line. You see this vertical first line right here with the timestamp of 6.98 milliseconds. This line can get a timestamp, what you see here. That means if I would change the 0 point, for example, on this point, I just have to shift my road data, measurement data to this line. I got 7.22, and I easily can get this timestamp by clicking on Get, and the timestamp will be copied out from the measurement curve to the 0 point. Now I have just to save the data set and go to evaluate the data set again. And after evaluation, I can load the new evaluated data, and you see the time shift from these two curves. For sure, the 0 point was quite good and correct at the first blue line, but you see really good the time shift and how you can handle it. Okay, now I'll switch over to the presentation. We have talked about the evaluation of displacement. We also have talked about the evaluation of the velocity, and we have seen the possibility to change the 0 point of the test data. And now it's we came to a quite complex type of evaluation. It's the evaluation of failure, because I will say to you, it's quite hard to get that right failure point, but we will see in software again. I will mention some points before to you. When we see this slide, what we can see here on this slide, on the left side, we have a diagram, a force displacement diagram, and this diagram shows you a puncture test of a fiber reinforced plastic, and it's a quite strange result, I think. And what can we see here? We see one drop on this area, and we see one big force peak in this area. The first peak is the interesting peak. Here is the test of the puncture test, and the second peak is just the buffer of the pendulum head, which have to bring the energy in the system, what is not needed at the test. So we buffer the pendulum head on the counterbearing side. And there are several opportunities to fix this problem, that we got to the right curve, what we see here on the right side, what we really want to have to evaluate the test correctly. So afterwards I will show it to you in the software live, how we can change from the left result to the right, what we will get. What we have to do is to set the limit of the angle what we will evaluate in our pendulum test, and we have to decide a force drop what we will have to find an end of the curve. And if we decide the correct angle, the limit angle, and we decide the correct drop of the force, we got to the correct curve. I will show this on the software again. Okay, now we have changed the database, and this example was also on a fiber reinforced plastic puncture test on 4 meters per second. And if you have a look on the measurement curve, if you have a look on the measurement curve again, here we see a puncture test of a fiber reinforced plastic. Again, we have this small peak is the test itself, and here we got the impact of the pendulum head to the counterbearing system with our buffer. So what can we do to just evaluate this correct peak? We will open the data set of this test. We have a fiber reinforced plastic. As I have mentioned before, we have decided the puncture test at 4 meters per second. And in the failure evaluation, we got the default values. And with the default values, I will plot the result. You will see that it doesn't make sense. You can see the default values of the force displacement. And now we will change some settings. We have to change the alpha max of the single pendulum so that we don't evaluate up to -5 degrees. We just will evaluate up to -1 degree of the pendulum arm, and we will get to an end of the curve at a force drop at 50%, which is the norm parameter. We have changed these 2 parameters. We save this, evaluate the test again. And after evaluating the test again, I can plot the test. Now I can zoom in and we see just the blue line, and we got the correct end of the test curve. But now we will have a look on the failure point. So we have the correct end time at a drop of 50% of the force maximum, but now we have to set a correct failure point. And for sure, the software can't set the failure point automatically out of this measurement result. Because to understand this result, it's quite easy. It's easier to have a look on the test itself. I will show the video of the test that you can understand this result easier. Here you can see the high-speed video of this fiber reinforced plastic test. We got a very nice progressive failure image. Here we hit the probe, we got in a small load, and just starting on that point with a small crack in the middle, and got the quite progressive failure after here to that point. And what it makes easy for us that we have such a high-speed video, that we now can just take the correct timestamp out of the video, or we are just using the get function in the measurement curve. I will zoom in. Sorry. I have the first drop of this point is the first starting failure point. And with the function of get, I get this timestamp, save, evaluate the test again, and now have set correctly. For sure, I have to go to manual. I will do it again. Get the correct timestamp of the failure, save this timestamp, and evaluate the test again. And now we have set up the failure manually in the correct way. Here you can see the changing the symbol to a orange M. That means it's a manual failure setting, and we can change this symbol back to a failure. It's no pull through, and it's not a recovery. It's a failure. And now the data set of this puncture test is finished, and we got the result. Okay, this was the explanation of the failure setting. The next point is the stress strain evaluation. It's a quite complex point. I will show it to you in the software again. After the setting of the failure, we came to the setting of the stress strain evaluation. And as you can see in this example, we are still in the puncture test setting. There is no stress strain evaluation because we do not evaluate the puncture test in the stress strain evaluation, because therefore we would have to use a 3D TSC, for example, to get a strain field in the puncture test. But if we have a look in a 3-point bending test, for example, then you can see what we evaluate. We go to the stress strain evaluation, and the standard default evaluation in the 3-point bending is the non-elastic evaluation. But much more difficult is the evaluation of a tensile test of the stress strain evaluation. Here we are in a dynamic tensile test with some DSC information. And if we have a look in this stress strain evaluation, the default evaluation in our system is the true stress and true strain with mu measured. And of course, you can change from technical evaluation to the true strain evaluation, but it's always depending on which raw data do you have in your test, because this stress strain evaluation is depending on which information on raw data you have in this test. Okay, and the last point in this session, what I will talk about is about the results, what we directly get out of the of VALIMAT. If we have a look in the database, I will change in another database. So okay. Now we see VALIMAT again. I've changed to another database. And in this database, we have some 3-point bending tests conducted at from 3-point bending tests from fiber reinforced plastics and we have done some tests on different velocities on a static machine. There's a static 3-point bending test, dynamic 3-point bending test at 2.5 meters per second and on 3 meters per second. And if we just take this data, I have copied this data, and I will just copy this data to a new Excel file. I insert it, and I will show you a short possibility of the usage of an pivot table. I have inserted this data, and I will insert a pivot table on this data. Therefore, I'm using I will sort it by the velocity. And what will be a good output? For sure, it's the maximum strain, what I'm reaching, and the maximum stress would be nice. I change to the mean value. Okay, and now, and for example, also the Young's modulus could be interesting. And now in a quick way, we got a good short table with some interesting information out of a big amount of data. So we have the information of a material, of a fiber reinforced material in a 3-point bending with 3 different velocities, and we see that by increasing the velocity, the maximal strain decreases from 4 to 5 to 1 percentage, and the maximum stress goes up. So this is a really tiny and I think a smart way to use the data from VALIMAT here in Excel for a further evaluation. Okay, so now we have finished the evaluation of the test data sets. We have talked about the filter, the evaluation of the displacement, velocity, 0 point, about the failure, the stress strain evaluation, and how we can easily handle some results of VALIMAT. I hope I could give you some good impression how we deal with some measurement data, and we can evaluate this data, because this will be quite important for the next sessions, because just with right evaluated test data, you can get good material cards. And how we generate this material cards, you will see tomorrow at my colleagues Peter Reithofer and Benjamin Hirschmann. They will generate a MAT 187 material card, and for sure they will show you other material models. Okay, now I think we have some time for some Q&A. I really just will thank you for your attention, and we will wait until 11 o'clock, I think, to answer some questions. So feel free to contact us in the Q&A channel. So I will have a short look together with my colleague Christoph on the Q&A. So we got a question before the coffee break. What is the maximum traverse distance in the dynamic tensile test? That means the maximal displacement what we can measure is depending on the high-speed camera, I would say, but we can reach much more than 30 millimeters roughly. So we can easily handle 30 millimeter displacement. And it's always depending on if you have some materials which will reach very high deformation. You have to think about your tensile geometry, I would say. But we typically use the type 3 specimen type, and in the test what you have seen today, we are reaching nearly 200% of local strain. Another question on the dynamic tensile test is if we can measure a volumetric strain with our system. And I have to say that we do not measure directly a volumetric strain because we are using a 2D DSC system. That means we're just measuring the strain in a plane area. We are measuring the strain in two directions. That means we are measuring in X and Y axis. So we can calculate out of this strain measuring the Poisson ratio. And with this Poisson ratio, we can divide to the volumetric strain. We have also inserted the Microsoft Forms link in the Q&A area if you will have a look on it and to find this link. Okay, here we got some request to the export from VALIMAT to Excel, how this works. And I would say I will show it to you again, just here in the software, if you like. So I change to the software again, and there are several possibilities to get data out from VALIMAT to Excel. The first and easy possibility is just to mark the dataset you would like and use Control-C for controlled copy, and you have you can just insert your copied data to Excel. So that was the possibility with Control-C. Of course, you can use a context menu in our software with the right mouse button. And after the right mouse button, clicking the right mouse button, you go to database. Oh, sorry, you can't see it. I have to change the screen. You go with the right mouse button to database and go to export database values to clipboard. And so you have also copied the data. And I would say the third possibility is also a good possibility to get some results out of VALIMAT. It is the possibility to use Python scripts, as you can see here. Here we have some Python scripts which you can, some can be provided from us, and you also can create your own Python scripts and use these Python scripts to export data from VALIMAT in this format what you like to have. So we're using Python script, for example, the export CSV, but I would like to recommend you the last session on Friday, which Benjamin Hirschmann will talk about Python scripts, and he will show the possibility of using these Python scripts to export the data to a CSV file. And another possibility, a really cool possibility, is that we can, for example, plot some data. Now I have plot some banding data. Here we are in the force displacement diagram, and on this small arrow, you can go to data and go to copy. Now we have directly copied the force displacement data of this diagram, and we also can easily insert this data in Excel, for example. So we have copied the data and we insert this data, and we got the force displacement of this 4 test data sets we have plotted. And this method works with every diagram which we find here. Also, you can copy directly the diagram. So we don't use data, we use diagram, copy, and now we got a picture of the displayed diagram. I really thank you for your attention.